Okay, this is part 6 in our Taylor series and binomial expansion videos, and we're going to try to wrap up this business of how do we handle it when we have a binomial expression raised to a negative exponent. In the previous video, in part 5, we derived this expression. In this video, we're going to modify it a little bit into an expression that we're going to use quite frequently when we start dealing with generating functions. Now, just as a bit of notation, in our previous videos, when we deal with binomial coefficients, you see us write it like this. So this right here we can write as like this. And in this video, what we're going to show first of all is that this is equal to this expression. Now, remember from the previous video, from part 5, that this, that's equal to minus 1 to the k times n times n plus 1, and they keep increasing like this up until we reach n plus k minus 1. And this is divided by k factorial. Now what is this equal to? Just this part. Well, by definition, this must be equal to n plus k factorial divided by k factorial times this minus k and minus 1 factorial. What is the numerator going to be equal to? Here we have n plus k minus 1. Then the next number has a decrease by 1, so that will be n plus k minus 2. Then it decreases again for the next term. And we can keep going like this, but what happens then when the number that we're subtracting here is equal to k? So we keep going along, we'd have n plus k minus k. Well, n plus k minus k is just n. So the next term here has to be 1 smaller than n, so this is going to be n minus 1. And they're going to keep getting smaller and smaller until we reach 1. So you can say that this here is equal to this. In fact, let's just write the n in here. Times n minus 1 factorial. And down here we have k factorial times n minus 1 factorial. And these cancel. So this expression is equal to this. Notice that we start here at n plus k minus 1, and as we go to the right, each term gets smaller by 1 until we reach n. Or we could start at this end and say that each term increases by 1 until we reach this number. So let's write it like that. This will equal, we start here, that term is n. Here we're going and each number gets smaller by 1. If we go in the opposite direction, each number will get larger by 1. So the term next to this one must be n plus 1. So here we're starting here. The term right next to it, now we're going in this direction, so they get larger by 1 successively. So the next term right next to it is n plus 1. Then as we go along, we'll have n plus 2, n plus 3, and we'll continue until we reach this term here. And that is divided by k factorial. And that is what this is equal to. Well, if we multiply both sides of that equation by minus 1 to the k, that will equal minus 1 to the k times c n plus k minus 1 over k. And that is what this is, right here. So we have proven this expression. So now we want, this expression here is what we have just proven then. This is equal to this, and this is equal to that, and these two expressions here are the same. So let's erase this and see how we can use this to our advantage. What we have right now is we've shown that c minus nk equals minus 1 to the k c n plus k minus 1 over k. And this is equal to, we have this, minus 1 to the k. But this right here is the same thing as c to the n plus k minus 1 over n minus 1. In our previous videos where we dealt with combinations, we've shown this to be true. By definition, this is n plus k minus 1 factorial over k factorial times this minus k, that's n minus 1 factorial. Here, this is n plus k minus 1 factorial over n minus 1 factorial times this, subtract n minus 1. N minus n goes away, negative 1 minus negative 1 goes away, and we have k factorial. So what we're going to do is rewrite this by putting this in place of this. And then when we do that, we're almost finished, and we can show you what kind of a convenient expression that gives us. So we have minus 1 to the k c n plus k minus 1 and minus 1 a to the minus n plus k x to the k. Alright, what does this mean? And again, it's still an infinite series. K starts at 0 and it continues all the way on out to infinity. But to see what form this gives us, or what kind of expression we can derive from this, let's see. We'll start when k equals 0. That's 1. K equals 0, that's n minus 1. So we have the binomial coefficient of n minus 1 over n minus 1 times a to the minus n. That's 0, and x to the 0 is just 1. Okay, now we move on. K equals 1. This is a minus sign now. 1 minus 1 is 0, so we have this binomial coefficient, n over n minus 1. And for here, we had that k now equals 1, so we have a to the minus n plus 1 times x to the first power. Okay, let's go on to the next term. K equals 2. Minus 1 squared, that's a positive number. So we have plus 2 minus 1 is plus 1 now. So you have this binomial coefficient, n plus 1 over n minus 1, a to the minus n plus 2 times x squared. When k equals 3, this is negative, minus 1 cubed. So you have minus 3 minus 1 is 2, so we have n plus 2 over n minus 1. We have that binomial coefficient. Here it's going to be a to the minus n plus 3 times x cubed. And we can keep going along like this. Only remember now, we have an infinite number of terms. But you can see there's a pattern that comes out of here. Our first binomial coefficient, n minus 1 over n minus 1, this part never changes, and this part here continually increases by 1. This exponent here, a to the minus n plus 1, it continually decreases by 1, because here we have a to the minus n plus 2, so this negative exponent is 1 smaller than this negative exponent, and the exponent of the x term continually increases throughout the series. So this right here is probably the most convenient form then to write down the binomial expansion of a plus x when you have a negative exponent. And just two other remarks. If this is a minus sign in here, all of these terms are now positive. We don't have alternating plus and minus. All the terms are positive. And let's just take a second here and compare and contrast this for when we have a plus x to a positive exponent. Then, writing it out, we have the first term, this binomial coefficient, a to the n, plus this binomial coefficient, plus this binomial coefficient, and it keeps going like this until it's a finite series. This is an infinite series. With here, the numerator part of the binomial coefficient stays the same. With here, the denominator part of the binomial coefficient stays the same. But we took some time to derive this and to show it to you explicitly, because when we deal with generating functions, this will be a very convenient expression for us to use. Right here. Okay, that's all I want to say in this video. What we're going to do in the next video is use this to solve some problems, and then finally we can start getting to generating functions, and with that background then we can solve much more complicated permutation and combination problems that previously we have not been able to handle. And by the way, just as a reminder, if you can go to the website at digitaluniversity.org, all the videos that we have for combinations and permutations and probability problems, they're all listed in order there at the website. Okay, that's it. By all means, come back and join us for some more videos, and we'll start solving some more problems.